Alright, today we're going to be providing the answer to problem number 3 of homework number 1. The specific wording of the problem is prove or disprove if the probability of A conditional on B plus the probability of the complement of A conditional on the complement of B all is equal to 1. Given that, then it should be sufficient to show that A and B are independent of one another. We pretty much tell as much here in our given right here. That's our given equation that we'll be using, and we're going to be attempting to prove independence. How we're going to approach it, which I'll explain in the plan, is by using this corollary that's used to show independence. That if we can show this term is equal to the probability of A alone, using this equation right here, then we'll be able to show that we have independence. That we have sufficient information in here to prove independence. If we cannot prove this, then we disprove that independence exists between A and B. And I basically said as much right here. Using this equation, that's basically what I said. So, we start by using this equation right here. We can see that just by general manipulation, putting this term, subtracting it from both sides, we can get this term right here. Alright. Then, after we do that, we can see just by the definition of conditional probability that this part of the equation can be converted into this, right here. Combining the terms, like basically, instead of using one, using probability of complement of beta over the probability of complement of beta, we can combine terms. We end up with this term right here. Now, starting here, we get a little bit of interesting. If we think about it, the probability of the complement of beta is basically 1 minus the probability of B beta itself. Makes perfect sense. It kind of goes along with the definition of complements. We thus are able to substitute this term in here on the top of the numerator as well as the denominator. Now, if we look at this intersection term of the two complements of A and B, we can actually figure out that we can substitute this term with this term right here. That basically the intersection is equivalent to 1 minus the probability of the union. And if you draw this out in Venn diagrams, it makes perfect sense. If we then bring through the negatives, do some simple arithmetic, cancel out ones, we end up with this equation right here. Remember, this is all derived directly from here. We haven't done anything else. We haven't made any changes. This is basic manipulation. Now, given this term right here, we can break it down further into, instead of just the sum of A and B, the probability of that, we know that we can break it down as the probability of A plus the probability of B minus the probability of the intersection term. So this term right here gets substituted for this term right here. All the other terms come down. As we can notice, the probability of B's cancel out. And we get this equation right here, which is basically the probability of A minus the probability of the intersection of A and B over 1 minus the probability of B. Now, why is this equation important? Well, as I can explain in the conclusions, given all of this is derived from here, we made no assumptions. We were just trying to see if we can get this from that. So what did we get? If we just use that, we're able to get this term right here, which is the same here. The problem is this term right here, the only time that this equation breaks down and we can actually get the probability of A out of that is when specifically the probability of the intersection is equal to the product of the individual probabilities. Alright? And we can see this if we actually make this assumption, plug it into our equation right here. You can see we get probability of A. However, this is an assumption that we cannot make. Alright? Given the fact that we can't make this, we start to see that our original given is insufficient to prove the independence of alpha and beta. Thus, we disapprove the presence of independence.